Welcome everyone to our very first lecture of our FSE10021 Foundation Chemistry. And let's talk about some basic concepts for this chemistry lectures that we will be talking about. And at the very beginning, we will talk about the structure of atom. So for this lecture, our objective, that what we want to learn from it, are to calculate the average atomic weight. This is generally denoted as AR of an element given the relative isotopic mass and percentage of abundance of any atom can be different. It might have a relative different of masses, but at a certain number of mass, we have to express it for our better understanding. So we will discuss it a bit more in coming slides. Okay, so number two, we will be calculating the empirical formula and molecular formula of chemical compounds. What is empirical and what is molecular formula? We'll see the definition of it also. And of course, we will need to convert between moles, number of particles, or number of substances that we have for calculation of chemical calculation that will be required for chemical calculations. So, structure of atom. So, for an atom, for our understanding, just for an example, we can consider that. Let's consider a big crystal ball in that we see in our some fortune teller's hand, right? A crystal ball that we can see through. So in that crystal ball, at the center of that crystal ball, in space, in vacuum, there is a very small substance occupying, very small amount it is occupying, but it has the maximum mass. It is very dense, very heavy matter or substance that is occupying at the center, and that is called the nucleus. Okay, that is called the nucleus of the structure of that atom, and in that nucleus there will be protons and neutron. So proton is positively charged, neutron will have no charge, so it is neutral. You can also see from the nomenclature that proton is positively charged, neutron that is neutral, and around it, throughout that sphere, the volume of the sphere, there will be a lot of electrons moving around this proton or the nucleus. So that electron is not bound or is not stationed to any specific space, but rather they are moving around all through those crystal balls, the volume of the surface of the crystal balls, it is moving all around. So that is the electron cloud. We can find the electrons in that electron cloud. Okay, so that is called the electron cloud, right? Now, how do we describe the atoms? Well, there is the atomic number and mass number, because we have already seen that the nucleus, it has proton and neutron. So the number of the protons in an atom will be always same. So you can say that the number of proton is its IC number or its passport number. That it cannot be shared, it cannot be similar to others. So one one atom should always have a certain number of proton, and that is its identity, right? And okay, and then mass number, that is the total number of proton and neutron. Okay, so proton number is added to the number of neutrons it has in the nucleus, is the total mass number. And this mass number can be similar to others. We can find some other isotopes of the same mass number, but proton number cannot be changed. So if we look at in the periodic table, we will see that there is a number of protons, is atomic number is showing at the bottom, and on top is showing the mass number for that atom. although this expression varies with the different expression or different type of periodic table what we're looking at. Just for example, here we see that one periodic table that you can find from ptable.com on the website. You see that here, which one? Okay, carbon, right? We see carbon, nitrogen, oxygen. Here it shows the number of proton. Here it is showing on the top, and its atomic weight or mass is showing at the bottom, unlike what we have seen in the our lecture slide. But this type of expression is also very common. We can see it from different periodic table. If we look at the different periodic table, we will see it in this way. Okay, so for this carbon, we see here it has 12 total mass number, and it has an atomic number of 6. That means it has 6 proton. Okay, so it has 6 proton, and when we see that number of proton is positively charged and electron is negatively charged, so if that atom is neutral in charge, that means it has equal number of proton and electron together, because they will have to cancel the charge each other. So the proton positively charged and electron negatively charged will cancel each other. For this, we see that carbon is neutral here. There is no charge shown on it. That means it is neutral. So it will have equal number of positive charge and negative charge. And that is how they are having the positive and negative charge. That means 6 proton it has, and also it has 6 neutron as well, electron as well. That means they have equal number of positive and negative charged. So one example for this atomic number and mass number for different um, elements and their different status. If we want to see, let's see the example of for chlorine and iron. Chlorine, if we see from the periodic table, we will see that it has 17 protons, right? It has 17 proton, and then this number of proton is telling us that it is a chlorine. It cannot be anything else. Its proton number 17 is chlorine. So, but it has a mass number of 35, and another time it has a 37, the mass number. So this is two different mass numbers. So what is the thing going on in here, right? So of course proton is number 17, and the mass number, we know that the number of proton plus number of neutron is the sum of neutron and proton is the mass number. So if we deduct from this 37, 35, 17, we will get 18, which is the number of neutron. So for this, we have proton 17 proton, but we have 18 neutrons, and neutron does not have any charge, of course. So another thing, we see that here for this chlorine, it is negatively charged. There is a negative charge on top of it. That means it is not a neutral. It has a one negative charge. But for this, it does not have any negative charge. That means it is a neutral atom, right? It's a neutral atom. So when there is a neutral atom, that means there is no extra charge. That means the positive charge of proton and the negative charge of electron has been cancelled out. That means they are equal number of proton and electron in the atom. So of course there will be 17 electron as well. But for this case, chlorine negative one, that means there is one negative charge. So when there's one negative charge, that means it has one extra electron than the number of proton it has, and that is the excess of electron is causing it to be negative. So we understand that 17, of course, the number of proton, and it will be 18 electrons in it, and that is why it becomes the negatively charged. But neutron number, again, this is the difference between the mass number and atomic number. So for this we have 20 neutrons for chloride 37, it has 20 neutron. Again, for iron, Fe2, iron 2 plus, when it is 2 plus, that means it has 2 positively charged. It is also not neutral, and it is positively charged. Electron is negatively charged, so when electron is added up, it increases the negative charge, and when it is deducted, when it's taken away from the atom, they so the positive charge or number of proton increases, so they become positively charged. The atom becomes positively charged. So for this case, of course, this is the number of proton, and this is the passport number for iron. So 26, it cannot be changed. For iron, always 26 number of protons are there, but number of neutron is the mass number minus atomic number, so it is the 30, and since it has 2 less electron than the number of proton it has, so we will have 24 electrons in this iron 2 positive charge atom. Okay, so another thing, this table is telling us that chlorine, there are 2 chlorine here, these 2, chlorine 35, chlorine 37, so they are the isotopes. Okay, they are the isotopes of chlorine. Okay, so they are the isotope of chlorine, and we can see the chlorine, that status or the position of chlorine on the periodic table. If we look at the periodic table, we will see that chlorine is lying on the group number 17 in the modern periodic table, or 7A. So if we see from this periodic table, this is this 1, 2, 3, 4, 5, 6 all together until 18. These are called the groups. Okay, these are called the groups. So chlorine, fluorine, chlorine, bromine, iodine. So these all are group 17 elements. All right, so here this is the number, the group, and this one on the left side, on your left hand side, this is 1, 2, 3, 4. These are called the period. So we know that chlorine is 17 group, but it is on third period, 3 period element, right? So 3 period element is sodium, magnesium, aluminium, all are 3 period, but only chlorine will be 17 group and period 3 element. So another thing, since we are in the periodic table already here, let's talk about the element that on 18, group 18, there's the helium, neon, argon, krypton, xenon. These all are noble gas. They are noble gas. That means their octet is filled up and they are very stable. They do not want to react. They do not react. They are very stable. They want to stay as it is, right? So all are the elements in the periodic table except those noble elements. All of them want to be like this noble gas. They want to attain the electronic structure, number of electron. They want to have the similar number of electrons, same number of electron of those the noble gas has, right? So fluorine has 9, always want to get 10. Oxygen has 8, always want to get 10. Lithium has 3, it cannot get 10 because to get 10 it will have to get 7 more electron. That is very difficult. So what is easy is it can become like helium by giving 1 electron. By releasing 1 electron from 3, it will become like helium. So some of them want to release the electron, some of them want to get the electron. All the metal, all those metal that we have, these are all metals, right? So they always want to release the electron and try to become like some of their noble gas structure. But all this gas that we have, non-metal, all these non-metals we have, they want to get one electron. They want to take one or many more electrons to become like this noble gas structure. We will see it in a while a bit more. Okay, so we see that chlorine is lying on this group 17 and period 3 element. So since we see that another thing to remember, that chlorine has the atomic molecular what is the mass is 35.45. This is the mass, but we have seen it is that the mass for this is the sum of proton and neutron. But why there is a fraction? Proton and neutron cannot be fraction. So why there is a fraction? Well, it is coming because they have different isotopes in the nature, and these isotopes occur in a different percentage in nature, depends on the condition of nature, the temperature, pressure, and many other things. So they stay in different percentage. That is, the average of all those percentage is called the relative atomic mass. That the mass is expressed here is the relative atomic mass of all the isotopes it has. For all of the elements, they have isotopes, and the mass is the relative of all those, the average of all those isotopes available for them. So how do we find the relative atomic mass for this? There is a equation for this, formula for this, to find the relative atomic mass for an atom. It is that is AR equal to percentage of abundance times the atomic mass of that isotope. Okay, because the percentage of abundance is how much percent of that specific isotope is staying or can be found in the nature by the total number of percentage of abundance of the element. It will be a bit clear when we go to the next slide. So here it says that calculate the relative atomic mass of chlorine given that it consists of two isotopes. Actually, chlorine has three isotopes, but these two are the major. The another one is very small amount, so it's not counted. So chlorine 35 and chlorine 37, and with the percentage of abundance is 75.91% and 24.09% respectively. So chlorine 35 has a percentage of abundance in the nature is 75.91% of chlorine 35 you can find in nature, and 24.09% of chlorine you can find for chlorine 37 in the nature, right? So this one, how do we express in the average relative atomic mass for this? Okay, so 35, as by the formula that you have seen, 35 times the percentage of abundance that we have in the nature, that we find from the nature, that is 75.91. So we multiply this and then we sum up with that the same thing for chlorine 37, that is 24.09, and we divide by the total number of percentage of abundance. So total number of percentage of abundance, mostly maximum time it will be 100%, but sometimes there is small percentage not considered, so maybe it will be 99.99 something. That is also okay. So altogether we find that it is the relative atomic mass for chlorine is 35.5, and this is the mass that it will be, you will find it on the periodic table. Okay, so percent by composition of mass, there is another example or another aspect that we have to consider, that water, H2O, we know that is water, right? So how many percent of hydrogen is in water, or how many percent of oxygen in water? So this is how the percentage composition by mass, we have to find it. It is also important for us to know. Like magnesium oxide, this is MgO, is the magnesium oxide, and if it is asked that, okay, how many percent of magnesium in magnesium oxide? Okay, so we have to know the mass, the atomic molecular mass of magnesium oxide. From the periodic table, we see that magnesium is 24.3 from the periodic table, the relative atomic mass for magnesium, and for oxygen it is 16, right? 15.9999, but we can just round up to 16, so it is 16. And we it is the magnesium mass of magnesium is 24.3, that is, we have taken it, so 100%, so 60.3% of this magnesium oxide is magnesium. Actually, for whatever percentage or amount you take of magnesium oxide, 60.3% of that magnesium oxide is actually magnesium. The rest, that is 29.7%, 39.7%, is oxygen in the magnesium oxide. So there is another important thing, that empirical and molecular formula that we were talking in the beginning, that empirical formula is the simplest whole number ratio of atoms of different element in the compound. Like what type of element are there, and to one of the element to another, what is the simplest ratio we can express? That is the empirical formula. But the actual formula is the molecular formula, that we understand how to express, and by expressing or by looking at the formula, we know, okay, this is this compound, right? So that is the molecular formula. So there are two ways the molecular and the chemical formula you can express. One is empirical formula, another is molecular formula. For example, there is glucose. Glucose, the molecular formula, that if we look at it, we will know this is the glucose, or there are 6 carbon in it, 12 hydrogen, and 6 oxygen atoms in the molecule. But if we divide by 6, or express it in the simplest formula, like 6, 12, 6, not in this way, just as the simplest way, if we want to divide, take the ratio, we will see that, okay, carbon and oxygen here is 1 equal ratio, but hydrogen to carbon or hydrogen to oxygen is double. They have double hydrogen than oxygen, or double hydrogen than carbon. So this is the empirical formula, that is the simplest ratio of the whole number. We cannot express it in fraction, like if there is any molecule, and if it is 0.5 or 1.5, we cannot express in that way. We have to express in the full number or whole number. So we can actually find from empirical formula to molecular formula, or from molecular formula to empirical formula, vice versa. So one example, calculate the empirical formula of an oxide of lead, that is lead oxide, okay, which contains 86.6% of lead. It says that 86.6% of lead we have in lead oxide, right? So how do we find the empirical formula, that is the simplest ratio of elements in that molecule? How can we find it? Okay, so it says that 86.6% of lead. Let's consider that this is, for it is the actual weight. So we have 86.6 gram. Let's say that it is the weight of that lead. So if we have 86.6 gram of lead, okay, so then we have 13.4% of oxygen. If 100%, right? Well, 100%, so 13.4% of oxygen we will have out of 100%. And now we are considering that this is actually a whole is weight. The gram is 86.6 and oxygen is 13.4 gram of oxygen is there. So number of moles, we'll find it. We will divide the mass, that is in gram, by the molecular weight of lead. And the molecular weight we can find from this periodic table. if we go to the lead, and we will see that it has the molecular weight of lead is 207. We see that it is 207. Where is it? Anyway, so is we cannot see. We can see that on the corner, right, left corner, that lead is showing that is 207 is molecular atomic weight. It shows. So we divide this the gram, this is the mass, by the molecular weight, then we find the number of moles. What is the number of mole, or what is the molarity, we will later coming in the next slides. But okay, for this we will find the number of moles is 0.418 moles of lead it has. In the similar way, we find the number of moles is 838 for oxygen. So we divide this 13.4 by its molecular weight, or for this case atomic weight, right? So 16 is its atomic weight. So we divide it and we find this is the number of moles is 0.838, right? Now we have seen from the definition that the ratio has to be whole number. It cannot be an integer. It cannot be a fraction. That means it cannot be a broken number. It has to be a whole number. So how do we find the whole number? If we find this type of problem, that this is a fraction, we are having a fraction. So what we will do is we will divide by the two numbers, both number, or if we have many more, right, many polyatomic molecule, so we will have more, maybe here, maybe lead, oxygen, hydrogen, whatever, and if all of them are fraction, we will divide by the smallest number. Okay, among these two, this is 0.418 is the smallest number. 838 is bigger than 418. So we will divide by the smallest number, both the fraction with the smallest number. That is the 414. So of course it will be 1, and if we divide, it will be 2. So now we see that this is a whole number. It is not a fraction anymore. So oxygen is 2, lead is 1. So lead is 1, oxygen is 2. Just for your information, that if we do not find it is a whole number yet, like 1.5, let's say that it is not 2, it's 1.5. So what we would do is we would multiply by 2 on both sides until we get a whole number. Okay, so if it's 1.5, then we will multiply by 2, this side also 2, this side also 2, and we'll get 3 here, and it is 2 here. So in that case it will be Pb2 and O3. Okay, so just for information. And if it is 2.15, a very small amount, then we can just round up to 2, and same goes for here as well. Okay, so from the empirical formula, how do we find the molecular formula? Okay, so there is the formula for this. So if we find the relative molecular mass for this molecule, that we have the empirical formula, we divide by the empirical formula mass, right? So for this, if the empirical formula of certain carbohydrate is CH2O that we have seen previously, and the relative molecular mass of the compound is 180, what is the molecular formula for this? So relative molecular mass by empirical formula mass, unit mass, 180 we already have seen from this, right? So molecular mass of the compound from here is given, we found it, and the CH2, this is the empirical formula for this carbohydrate. Carbohydrate is CH and O because there's carbohydrate. So for this, we find this the mass for this CH2 will be, carbon is 12, hydrogen is 1 or 1.01 to be precise, and there are 2 atoms of hydrogen, so multiplied by 2, 1 atom of oxygen, so plus 16, because oxygen 16, carbon is 12. So we divide and we find that n, this number of n is 6, right? And then we multiply this formula with 6, and then we find the molecular formula for this carbohydrate. Writing the chemical formula, it takes a little bit more depth knowledge to write the chemical formula. Okay, for magnesium chloride, if we see from the periodic table that magnesium is in period group 2, is a group 2, so it will have two positive charge, and magnesium is metal. So all metal will be formed positive charge. So it will be 2 positive charge. If it is scandium, it will be 3. If it's titanium, it will be 4, and so on. So there are exceptions, of course. So later we will see more about it. But for this case, magnesium, there are 2 positive charge because it's in group 2. So, and chlorine is a non-metal, so it will be negative charge, and chlorine is always one negative. So magnesium and chloride will be formed in this way, and then we see that magnesium has 2 positive but chloride has 1 negative. So to neutralize this 2 positive charge, chloride, there will be needed 2 chloride, right? So each one charge will neutralize one. So 2 chloride, the 2 negative charge will come from 2 chloride. So this 2 positive charge will be neutralized, and that is why this 2 is shown here. So it is magnesium chloride. Same goes for iron 3 positive charge, and sulfate, it has 2 negative charge. So 3 positive charge has to be neutralized by this negative charge. How we can become 3, because this is this number is not like this, straightforward, 2 and 2. So we multiply by this 3 charge, so it becomes 6 positive charge, right? 2 times 3 becomes 6, and also we multiply the sulfate by 3, so this 2 negative times 3 becomes 6. So 6 positive charge, 6 negative charge from 6 from this amount of ions. This is ion because they have charge, so they are ions. So these ions, and they form the bonding, and they produce Fe2SO4 3. So iron 3 sulfate, and this same goes on in this way. So for more of this common list, ion list, you please visit this link at the below the screen, bottom of the screen. Now, name of some formula and common polyatomic ion. Polyatomic ion because when there is more than 1 or 2 atoms in that ion, so there are polyatomic ion, because here we see that nitrogen and hydrogen is there. We see carbon and hydrogen and oxygen are there, so these are polyatomic. They are polyatomic ions. So this is a cation that is called ammonium ion, and this is acetate ion. This is coming from acetic acid. This acetic acid, take good care of it, because this acetic acid, we will talk a lot about it later. This is carbonate ion. This is chromate ion, sulfate ion, chloride ion. In this way, we can find the name. And for this naming, there will be not much help other than you just be familiarized with and become comfortable with the names of this. Please go through all of it and try to remember the names. It will be easier to understand many of the chemical equations later on, to understand faster. All right, the number of moles or the mole. This is just a name for a collective unit, just like a pair or a dozen. Or we say that in a dozen we have 12, in a pair we have 2, in this way. it is just a collective unit for a bunch of or a number of different object or particles or different things, substance, right? It's the number of substance, amount of number of substance is defined by mole, and this number is always constant. This is Avogadro's number, 6.023 times 10 negative 10 to 23rd. This is the Avogadro's number, and in 1 mole there will be always this amount of those substance. Actually, this number comes from the 12 gram of carbon 12. Carbon has different isotope, 12, 13, and 14. But in 12 gram of carbon 12, this amount of carbon atom will be there. Alright, so this is the Avogadro's number, and in any number of moles, this amount of those substance will be there. So in a mole of oranges will always contain this number of oranges, and it's a huge number. Actually, it's a very big number. So this number, I mean, 1 mole of orange contains 6.02 times 1023rd oranges, just like 1 GB, that internet we use, the 1 GB is 1024 megabyte, right? It's always 1 GB means 1024 megabyte. So that is how 1 mole of megabyte, we will always have 6 times 023 times 10, 6.023 times 1023rd more megabyte of data. That means 1 mole of this data megabyte is always this number of so this is just a number to express a group or unit. Okay, so 1 mole of oxygen molecule will contain this number of oxygen molecule. Okay, 1 mole of oxygen is this number of oxygen molecule. 1 mole of electron will always have this number of electrons in it, right? So this is the number of moles. So Avogadro's number, in any mole, 1 mole always be there will be always this number of those substance. So molar mass of sodium chloride is 58.443 gram per mole. That means in 58.443 gram, if we weigh it by using a balance, okay, let's say we have a very sophisticated, very precise, very good type of balance that we can exactly weigh this amount of sodium chloride. Sodium chloride is our table salt, right? We can weigh this 58.443 gram of our sodium chloride. We can be certain that it will have this Avogadro number of individual sodium chloride molecules. Okay, so this number of sodium chloride will be in this gram of sodium chloride. So this is whatever, when we say that a mole, 1 mole, we understand that, okay, it has Avogadro's number of particles or substance in it. So there are some formulas that will be very important for us to remember and to work out, and please go ahead and try these formulas and get used to it, because these are very important and it will be used for our many calculations and processes later on that we will discuss.